So let's review how we find the molar free energy of formation for an oxide and what we already know about this. So we want to consider, for example, reactions that might look like this. Si plus O2 forming SiO2, or Ti plus O2 forming TiO2. We could consider copper and oxygen forming Cu2O, or aluminum and oxygen reacting to form Al2O3. You'll notice that I've written these all to have 1 mole O2. And the reason why we do this is that if we write these all to have 1 mole of O2, then we can more easily compare the delta G of the reaction, where we're interested in sort of the condition of the O2 in the system. So we need to write these always with 1 mole of oxygen. The reason that we want to compare the delta G is that it tells us something about the likelihood of oxidation occurring. So if we have a generic reaction that looks like this, metal in a solid state plus O2 in the gas phase forming MO2 solid, we can write that the affinity is equal to delta G naught of that reaction plus RT times the natural log of the activity of the oxide divided by the activity of the metal and divided by the activity of the oxygen. If we assume that the metal and the oxide are pure, then their activities are equal to 1. If we assume that the O2 is ideal, then the activity is equal to just the partial pressure of O2. So then we can say that at equilibrium, remember A is equal to 0, Q is equal to K, and so delta G naught is negative RT ln of K, and we get our value of K from here essentially, and we have that K is equal to 1 over PO2. So delta G equals negative RT ln 1 over PO2, or we can simplify this, right, and get delta G naught equals RT ln of PO2. Right? So this gives us then the equilibrium PO2 for any temperature, and we can find delta G as a function of T. So we want delta G naught as a function of T. Remember, we did this earlier in the semester where we looked at the delta G of formation or reaction as being equal to delta H of formation minus T delta S of formation, and we find this from integral, right, NCP dt, and this one from integral NCP over T dt. So we can do this, but we don't need to do it now. We can just essentially look up the tabulated values for delta G of the reaction as a function of T. So if we know delta G as a function of T, we can compare any two oxidation reactions to see which is more likely to occur. So consider now that we have a plot where this is delta G of the reaction, this is also defined as RT ln of PO2. Down here, this is more negative, right? So 0 is up here somewhere. This is a function of T. And so let's say that we have some reaction here, and this is A plus O2 forming AO2. And we have some other reaction, 2B, let's say, plus O2 forming 2 times BO. So because this B reaction has a more negative delta G, it is more likely to get oxidized, right? So this is more likely to occur, or it has a greater affinity for oxygen. In the next video, we'll take a look at how we can use this kind of a plot to actually find the equilibrium oxygen partial pressure for different systems.